I'm recording this video because I want to correct a small issue with the previous decision trees video. Most of it was fine, but there was one small detail which is kind of important when you're doing implementation, so I just wanted to make sure that this detail was spelled out. In particular, the example I worked out wasn't quite right because it didn't do this, so we're going to do a new example here. Okay, so recall what we're trying to do in decision trees. We're trying to choose at each node how to split it. In particular, we try to find a J star and a T star, or in particular, we try to find a J and a T, such that we split the points within this node into two different sets. That is, we find all the points in the set within this node, which have coordinate J being less than or equal to T, and we put them in one set, that's SL. And then we find all the points within the set whose value in coordinate J is greater than T, and we put them in another set, SR. So we partition our data within this one node based on coordinate J's value, whether it's less than or greater than T, into two sets, SL and SR. All right, and then the way I said it before is that you want to minimize the sum of the losses at each of these two children. That is the loss on set SL and the loss on the set SR, where the loss of a set, I guess we can state it again real quick. It's something like if you define E hat C to be the empirical fraction of class C in a set, then for example, L of an S can be equal to, say, summation over all classes P hat of C times 1 minus P hat of C, and this is the Gini or Gini loss. So where this P hat of C is defined with respect to S, so maybe you can even write it as PC of S, but we won't worry about that. That's not too big. It should be clear. So now the issue with this is this isn't quite right. What you actually need to do here is, instead of this, you actually have to weight the two ends by the size of the set. So you need here that this is weighted by size of SL, and this one should be times the size of SR. And often you'll see it written normalized by the two set sizes summed together, like N or size of SL plus size of SR. And same thing over here, but I'm not going to do that just because it's not really that big a deal. It's going to just be a rescaling, and it doesn't change what the argmin is. So in other words, we sort of weight our loss on each child based on how many nodes are at that child. And this is very important, as we'll see in this example right here. So I constructed this example, which is fairly simple. You can see that there's two features. Feature 1 is just going to be almost all the time 1. But there's a single case where it's a 0, and so you can kind of see if it's 0, then the label will be 0, and that's a pretty clear sign. Whereas on the other hand, there's these other ones where we have feature 2 has a lot of zeros and a lot of 1s, but you'll notice if you pay attention that the label is pretty well correlated with the feature, in the sense that you'll note that say 4 out of the 5 times when we have a 0 in feature 2, then it's going to be a 0 prediction. Whereas, and on the other hand, when we have a 1, we know 4 out of 5 times it's going to be a 1 prediction. So it seems like feature 2 is kind of intuitively a better way of predicting the label, just because it works for a lot more of the data, versus feature 1, which only works exactly one time, well, for basically one time, and besides that, you don't really make much progress. So intuitively, we'd like to prefer feature 2, but the thing is, if you don't do this weighting, then this without the weighting, this expression places a lot more weight on, or a lot more emphasis on, trying to get nodes which are as pure as possible. Why is that? Well, remember, for the Gini loss, and basically any loss you'll consider, if you have an entirely pure node, that is one where the labels are all uniform, then that gets a loss of 0, and that is very helpful because 0 is kind of the smallest number you can imagine, smallest non-negative number you can have. So yeah, that makes the sum of these two things a lot smaller if one of them is 0, because any non-zero value will often be larger. Like, let's just, maybe this might be a bit weird, but I'll just say that without the weighting, it really emphasizes things which are it really emphasizes pure nodes. And we're going to see that via an example here by working out this example. So let's first do it the wrong way. And that means without the weighting. So the wrong way would be as follows. So let's say if we split on feature 1, what do we do? Well, we're going to split on into whether it's 0 or 1, of course, in feature 1. And what we can do is just, if it's the left split, SL would just be just the 0. So SL would be just the 0, and therefore we would have a loss of 0. And then on the right side, it would be, what do we have here? Well, if we're looking at the 1 labels, then it correctly predicts, then we'll have basically 5 1s and 4 0s. So therefore, doing this sort of prediction, then we have 4 over 9 times 5 over 9. And if you want, you can put a times 2 in here because you're summing over the 2 different classes, but it doesn't really matter. So I'm going to leave out this factor of 2 just for simplicity, because let me elaborate on that. When you're in the binary setting, when you're doing binary classification, there's just going to be an unnecessary factor of 2, which doesn't really change anything. So we're just going to ignore it. So if you do this, then you have a value which is like 20 over 81, which is something like approximately 0.247. On the other hand, if you look at feature 2, which we kind of agree intuitively is the better feature, this one would have, say, if you look at the ones which are labeled 0 here, then this would have, so we're going to look at which ones have feature 2 being 0. That's this, this. And we can see that of these, 4 out of 5 of them are going to be 0, and 1 out of 5 of them are going to be 1. So therefore, we'd get the following calculation here. We get 4 over 5 times 1 over 5. And again, this is all using the Gini index here. And if you look at the opposite one, if you look at the 1s, then you'll see that it's basically the same story, except with the 1s and 0s flipped. So similarly, we have plus 4 over 5 times 1 over 5, which is equal to 0.32. So remember, what we do is we try to pick the split which has the minimum value, and that turns out to be doing this wrong calculation, feature 1. And the reason for this, maybe you can infer, is that this value is really, really small. 0 is really small, whereas this is, we have 0.16 on both of the children here, which is kind of small in comparison to this 0.247, but the fact that we have a 0 here really makes this one the clear winner. So yeah, that's kind of it's a sub-ideal behavior, at least for this specific case. But let's see what happens if we do it the right way. Well, all we have to do here is just weight things by the number of points which fall into that. So that's going to be, this one is pretty easy, feature 1. This is going to be 1 times 0 plus 9 times 4 over 9 times 5 over 9. And if you do the calculations out, this is something like 1.78 roughly. Whereas on the other hand, if you do feature 2, well, here it's an easier calculation. It's 5 times 4 over 5 times 1 over 5 plus 5 times 4 over 5 times 1 over 5. And remember where these numbers come from. This 1 and 9 comes from the fact that if we split on feature 1, we'll get a bucket of size 1 and a bucket of size 9. Whereas if we do splitting on feature 2, we're going to get equal size buckets of 5 and 5. And this gives us 1.6. 1.6. So you can see here, in this case, in the previous case, we had that feature 1 was the winner. But here we have that feature 2 is the winner, which is kind of more in line with what we'd expect. So yeah, just make sure you realize this if you're implementing a decision tree, that this is the right way to do it with this appropriate weighting by the node sizes.